Good morning. I'm printing some stuff off and I'll join you, or we'll start here momentarily. I have to figure out how many pages there are in this file. Okay, this should be good. Let's see. Later today, I'll be posting a new homework assignment for this class, and it'll be on sapling again. So, kind of on the lookout for that, and it'll be due, I don't know, sometime next week, something like that. It'll include free fall problems. So we'll be taking a look at those things anyway. So my work is printed. I can share the screen. I'll have to clean up a mess first. Last hour, I had my screen freeze for a little while, and the volume disappeared on me. If that happens again, holler, and I'll try to catch it before too much happens. Okay, let's see. We're looking at that screen now. This is stuff from the other class. Some more stuff from the other class. Dragster problem. And here's our formula sheets. We'll use those from time to time. So first problem, dragsters can actually reach a top speed of 145 meters per second in only 4.45 seconds. Calculate the average acceleration for such a dragster. Well, average acceleration has a definition formula, and this is actually the definition of average acceleration. It is V2 minus V1 over T2 minus T1, or more simply, it's just delta V over delta T. Change in velocity over change in time. Well, the assumption here is, they don't state it, but the dragster starts with a velocity of 0. And so the delta V is going to be V final minus V initial over T final minus T initial. This would be T final. Our T initial in this case is going to be 0, or you could think of T final minus T initial as just the 4.45 seconds. So that'll be what's on the bottom. And this is a fairly straightforward application of the definition of acceleration. So meters per second minus 0 up there. And just 145 divided by 4.45. Again, the units that we use in the US will end up being meters per second squared. And it's a pretty good acceleration. I get about 32.6 meters per second squared. A little bit later in the quarter, we'll study friction, and there has to be a lot of friction between the tires of the dragster and the drag strip in order to produce an acceleration that big. That's actually 3 times the acceleration due to gravity. You would definitely feel that. You'd be pinned back against the chair and the thing. So that's pretty amazing. Then it says, find the final velocity of this dragster starting from rest and accelerating at that rate found in there for 402 meters without using any information on time. Okay, well, we've got a bunch of different equations and that we can use. So here are our constant acceleration equations, and I'm just going to write them down here. One thing you can write is that x is equal to x naught plus v bar times t. Now, this is an equation that we usually use when we have constant velocity, but if you're using the average velocity, this one works. But we don't know that one here, so it's not going to apply. And then something else, the average velocity is always just, or no, when you have constant acceleration, the average velocity is v naught plus v divided by 2, or the average velocity for some interval is just the average of the beginning and starting velocity. But that's only true when you have constant velocity. Excuse me. Now, more generally, when you have acceleration, you've got v is equal to v naught plus at. So there's one that works. And then we've got that one for x. X equals x naught plus v naught t plus 1/2 at squared. So there's another one of our equations, but I'm supposed to do it without using any information on time. And an average velocity isn't going to help me here. So let's see. Can't use that, can't use that. Have to use that one that doesn't involve time that I gave you yesterday. And anybody try that algebra-wise? Algebra lovers out there. Somebody's got to love algebra. Let's see. Anyway, it's this expression, 2a times x minus x naught. Okay. That's one that does not involve time. So let's figure out the final velocity of this dragster. By the way, the final velocity, I'll just have to take a square root here. So let's see what that equation will give us. I would have v equals the square root of v naught squared plus 2 times a times x minus x naught. That's the distance traveled. So I just plug in the numbers that I have here. Okay. Well, v naught is actually 0. It starts from rest. So starting from rest tells me that v naught is equal to 0. So inside here, I'll just have 2 times the acceleration, 32.6 meters per second squared, times, let's see, delta x. That's the 402 meters they give me. And I think that's all. Okay, just plug in the numbers. So v equals, and I'll show you, I would do this, I'd go, first thing I'd do, I'd hit second square root, so I'm working under a square root, and then just 2 times 32.6 times 402, and that's it. Then I get 162 to 3 significant figures, meters per second. Unit-wise, under the radical, I would have meters times meters per second squared. So meters per second squared times meters, those equal meters squared per second squared. But when you take the square root of that, you get meters per second. Okay, so the question here is, why is the final velocity greater than that used to find the average acceleration? Well, if the thing can, when it had that speed of 145 meters per second, that wasn't necessarily the end of the acceleration. Maybe it continued to accelerate. We didn't figure out how far it went during this time. So we don't know that. Actually, we could figure that out. If this was a constant acceleration, we could figure out how far the dragster would travel while accelerating from 0 to 145 meters per second. In fact, I can use my x equation to get that. X is equal to x naught plus v naught t plus 1/2 at squared. It's starting from rest, so I'll put an arrow with a 0 on it for that one. I'll put an arrow with a 0 on it for that one, and just see how far it traveled during these 4.45 seconds. And 1/2 times the acceleration, 32.6 meters per second squared, times 4.45 seconds squared, and I'd get a value for x for that particular thing, 0.5 times 32.6 times 4.45 squared, and I only get 323 meters. So it only traveled 323 meters while accelerating to that speed, but they didn't say that was the final speed. It may have continued to accelerate for the next however many meters there are between 323 and 402. So that's why it has a greater final speed here than it did with that other thing. Okay. Is the assumption of constant acceleration valid for a dragster? Probably not. Something that happens when dragsters first start up is they tromp on the gas and their wheels actually spin for a while with the dragster barely moving, and eventually the wheels will basically grab the road, grab the drag strip, and then that's when the acceleration really takes off, and or when the dragster really takes off. And so things aren't all that uniform during the motion of a dragster. The acceleration actually for a short time at the beginning is close to 0 because the wheels are spinning and it's not moving forward very fast at first. Okay, that was a pretty good one. Okay, I remember watching the 2008 Olympic Games on TV, and world record was set for the men's 100-meter dash by Usain Bolt of Jamaica, an amazing runner. He just left everybody behind. Well, that's why he won. Anyway, 100 meters, and this would be a very precisely measured 100 meters, by the way. This is probably good to just about the nearest millimeter, I think. So 0.001 or 000, something like that. Bolt coasted across the finish line with a speed of 9.69 seconds. If we assume that he accelerated for 3 seconds to reach his maximum speed and maintained that speed for the rest of the race, calculate his maximum speed and his acceleration. Okay, this is a complicated problem. It splits the race into 2 parts. There will be a part during which he accelerates uniformly, and goes from 0 to whatever his top speed is. And then there will be a stretch of time when his velocity is constant, and he just maintains that for the rest of the race. And so it's a more complicated situation. What I like to do with something like this is kind of make a sketch of what's going on. One thing that's nice for this is you can make a velocity versus time curve. And velocity versus time, he starts off with 0 velocity and has acceleration for some period of time. So this would be the uniform acceleration. And on a velocity versus time curve, the slope of the graph is the acceleration. Okay. Then he runs at constant speed for the rest of the race. And so what I would do in this case is just draw a flat line there. V equals constant for the rest of the race. Now, in real life, there's probably some sort of a little bit of a curve to this thing, but for our uses, we're going to say that suddenly, instantaneously, he just starts running at a constant speed once he's reached his final speed. If you make a sketch of the position versus time, x versus time, starts off with 0 velocity and accelerates to some final velocity. And this is a curve. That's what you get when you have acceleration. But then from then on, for the rest of the race, he's traveling at that speed that he reached there, and straight line. So here is constant velocity, and I'll abbreviate velocity as VEL. And here I have constant acceleration. Okay, now something that I know is that at the end of this, his position is going to be 100 meters. So 100 meters here. At the end of the race, the time is going to be those 9.69 seconds. So this will be 9.69 seconds. And they said if we assume that Bolt accelerated for 3.00 seconds, so this is the acceleration part, as is this, 3.00 seconds, 3.00 seconds. And so, whoa, this looks pretty darn complicated. Trying to figure this out. Well, let's see what we can do. And let's consider the acceleration part. And see what we can do with this. The acceleration part, an equation that would describe his motion, is x naught plus v naught x, or v naught. I'll just use that. Sometimes we'll put an additional subscript on this thing of v naught x to let us know its velocity in the x direction. In next week, we're going to be looking at situations of two-dimensional motion where we'll have motion both horizontally and vertically, and then we'll call y the vertical direction, and we may use that. But since this is one-dimensional motion, we don't need that extra subscript here. So anyway, plus v naught t plus 1/2 at squared. Okay, so that's what's going on there, but I'm going to let x naught is 0. That's the starting line of the race. V naught is 0. You can't get a running start in a race like this. I don't know if you've ever watched those things. People will try to, and you'll see all sorts of false starts in these races and things like that. So x is just 1/2 at squared. Now, we don't know what the acceleration is, and we don't know what the time is. Oh, we do know the time for that, and we don't know how far they travel, but I'm going to say that I'll just call this x1. That's how far he travels while he's undergoing uniform acceleration. And I'll call this t1. And t1, we made that assumption that this is 3.00 seconds. And so we'll have that. Then we've got the constant velocity part. Okay, and for that, I'm going to call x2 the position at the final part of this, and that will equal x1, how far he had traveled during this part, plus that final velocity times t. And so this is a constant velocity equation. Now, there's another equation that I could have written for this thing that I haven't yet, but I'll bring it down here. And this time interval, I'll call it T2. T2, this will be the length of this second time interval. It's going to be 9.69 seconds minus 3 seconds. So 9.69 seconds minus 3.00 seconds, and that's 6.69 seconds. That's how long that lasts for. Okay, I know that if I knew what x1 happened to be, I could plug this in here. x2 will end up being 100 meters, good to a whole bunch of significant figures, so that's not going to be our problem. But I don't know this v final, and that's something that's handicapping me. And I also don't know x1, so I've got 2 unknowns so far, 3 actually, if you count the a there. So in general, you need at least 1 equation for every unknown that you happen to have. And so far, I've only got 2 equations, and I've got 3 unknowns. X2 is 100 meters. And I'm going to call it 100.00 meters and just figure that it was measured to the nearest centimeter. And I'm sure they would measure it even more precisely than that. So that's a centimeter. For these world championship and Olympic races, they measure the distances extremely carefully. Okay, there's one more equation I can get out of the constant acceleration though, and that is that v final, which is the maximum speed he reaches, is going to equal v naught, which is actually 0, he starts from rest, plus the acceleration times t1. And so maybe I can do something between these 3 equations to figure out the maximum speed and the acceleration. So I might be able to do something with that. Let's see if I could put a final velocity into here. I think I might be able to. Since v final is equal to this, I'm going to plug that into there. Yeah, and let's see what I get if I do that. X1 is 1/2 a t1 squared. This is something you have to do in problems sometimes. You just write down equations that you know, and I'll summarize these without anything crossed out. X1 is equal to 1/2 a t1 squared. I don't know x1, but I do know t1. X2 is equal to x1 plus v final times t2, and v final is equal to at1. Okay, so if I take this and plug it in there, and this and plug it in there, let's see what I get. I'll get that x2 is equal to x1, which is 1/2 at1 squared, plus v final, which is at1 times t2. Okay, now take a look at this equation. I know x2, that's how far he has to travel at the end of the race. I know t1, that's 3.00 seconds. And I know t2, that's the length of the second time interval, that's 6.69 seconds. And so I know everything in this equation except a. And I can factor that out of this side. So sometimes you have to use algebra on these things. So I'll have a times 1/2 t1 squared plus t1 t2. By the way, I had not figured out this problem before class today. And so I'm just kind of winging it here, but I think I can do this. And so the acceleration is going to equal x2, the 100 meters, divided by 1/2 t1 squared plus t1 t2. And now I can just plug in numbers. x2, 100.00 meters. One half t1 squared. Okay, t1 was the 3.00 seconds. So I square that, plus t1 times t2, which is 3.00 seconds times 6.69 seconds. And now I just plug in the numbers and see what happens. Okay, I'm definitely going to have to wrap that denominator in parentheses, but the numerator is okay. It's just a single number. So 100 divided by, hit my left parenthesis, 0.5 times 3 squared. Okay, plus, I haven't done anything else with parentheses in that denominator. I don't know if you can see it that way. But anyway, plus 3 times 6.69. And then I end my parentheses, and we'll see what the acceleration is. 4.07 meters per second squared. Okay, I know the acceleration. Now, the other thing it asked for was, it says calculate his maximum speed and his acceleration. I did the acceleration first. The final maximum speed is this v final. It is going to be at1, which will be 4.07 meters per second squared, times t1, which was the 3.00 seconds. And he's moving. And I get 12.2 meters per second. Okay, so there we have it. And that's part A. Any questions on that? I had to do a bunch of work to figure this out. Recognize that sometimes you can't automatically solve one of these equations. You have to combine them together once in a while. And so that's just something that happens. The second part of this problem says, during the same Olympics, Bolt also set the world record in the 200 meter with a time of 19.30. Do they still call it like the 200 meter dash or not? Or did they just call it the 200 meters? I remember hearing it called that when I was a kid, and they'd call it the 50-yard dash and something like that, and they always timed us for something like that. And the 100-yard dash or whatever. I had a kind of weird ability. Well, I played around with math a lot, but when I was in 8th grade in PE, they had us run a 50-yard dash, and I wasn't very fast in it. I was a slow starter. And I calculated one time, I ran the half mile in track, and I ran a faster average speed for the half mile than I did for the 50-yard dash. I just wasn't a quick starter. And so it goes anyway. But during the same Olympics, set the record for that. So with a time of 19.30 seconds, using the same assumptions as for the 100-meter dash, what was his maximum speed for this race? Well, if it's the same assumptions, let's see, like I guess we'd have to, kind of redo the thing again, except this formula should still work. X2 in that case would be 200 meters, and the 1/2 T1 would still be 3 seconds, but T2 would be 19.30 seconds minus 3.00. So let's see if that works. See what we get for his acceleration in that race and for the other thing. So, but since I've already gone through the work, and I did this just with variables, and so the variables should work. So the acceleration should be x2 divided by 1/2 T1 squared. By the way, what I just did, solving something in variable form first, is something that I kind of like to do. For one thing, it's less work to write a variable than it is a number with its units and the correct number of significant figures. But it also lets you sometimes reuse the formula. And so that's what I'm doing here. So I'll have plus T1, T2 there. And T1 is again going to equal 3.00 seconds. T2 will equal 19.30 seconds minus 3.00 seconds. So T2 is going to be 16.30 seconds. And X2 in this case is going to equal 200 meters. And I bet it's probably measured to at least the nearest centimeter as well. So I'll call it 200.00 meters. So I'll figure out the acceleration, and then the V final will again equal A times T1. So let's see, what was his acceleration there? X2, 200.00 meters. Whoops, cross out that decimal point, 200.00 meters divided by 1/2 times 3.00 seconds squared plus 3.00 seconds times 16.30 seconds. And I'm curious, is his acceleration more or less than it was before? Oops, turn on calculator first. So 200 divided by, wrap that denominator in parentheses, times 3 squared plus, where's my plus? My one gripe about these calculators is these silver buttons. It's hard to insert in light And depending on how it reflects, you can't read what's on them. So I put this white sticker over here to help me out. Three times 16.3. Okay, I get a smaller acceleration this time. He had 4.07 the first time. I get 3.75 meters per second squared for this one. So didn't accelerate quite as much, probably because it's 200 meters long. If you tried to get going as fast as you did for the 100-meter dash, you'd crash. So V final is equal to AT1, 3.75 meters per second squared, times 3.00 seconds. I don't know where I'm at. Just multiply that by 3. And by the way, I had more figures on this one, and I left them in when I multiply this by 3. So I may get a slightly different number than you do if you just took 3.75 times 3. I get 11.2 meters per second for his maximum speed in that race. So we have that. Okay, there. That was a kind of two-part problem. This idea of combining equations is something that occasionally you will have to do, and it can be challenging. All right, let's start free fall, and we won't go too far with it today, but I just want to present some ideas. On the formula sheet, well, for free fall, the idea is at first, we're just going to have vertical motion, and this may be the ground here, okay? And we'll have motion either up or down in a straight line. I accidentally drew an angle there, but vertical motion. And we will let y be our vertical direction. And so we'll use that. Now, if I was to write my acceleration equations for x, they had things like x naught plus v naught xt plus stuff like that. I'm going to do the same thing for y. I'll have that y could equal y naught plus v naught yt. Now I'm starting to put an extra subscript on there just because we may sometimes have horizontal and vertical motion like next week. And then plus 1/2 at squared, and I could have v sub y equal v naught y plus at. And I could have that other equation. I'm not going to write down the average velocity equations, but I could. I'll have v sub y squared is going to equal v naught y squared plus 2a times y minus y naught. And so I can have stuff like that. Now, in the case of free fall, free fall, all right. The acceleration is going to equal minus little g. And little g is the acceleration due to gravity. It's the magnitude of it. It is 9.81 meters per second squared. And I've got a minus sign here because the acceleration is downward, and I chose y to be positive upward. And so that's something that I have on these particular problems. So that changes. When the acceleration is this minus g, it'll change my equations into looking like this, and these will be my free fall equations. Y is going to equal y naught plus v naught y t minus 1/2 gt squared. Okay, when the acceleration is negative g, that makes this have a minus sign in front. The v sub y will equal v naught y minus gt. And let's see, this one becomes v sub y squared equals v naught y squared minus 2g times y minus y naught. And in all of our free fall problems, we're going to know what the acceleration happens to be. It's going to be the acceleration due to gravity. By the way, we ignore air resistance when we're solving these problems. Okay, if we took air resistance into account, things would get too complicated too fast. Now, you can get away with ignoring air resistance if you're doing something like dropping a rock that's a fairly good sized chunk, or a solid steel ball bearing. If you drop it over a distance of, even if you drop it from a height of 150 meters, air resistance wouldn't play a very large role. If it was a tiny BB, it would, but if you used a, like say a shot put, you wouldn't have to worry about air resistance for something like that. So those are things that we'll do. And let's see, I'll just make up a free fall problem and show you how this might work out. And this is something that I actually did one time. So a physics instructor on vacation in Oregon drops a rock from a bridge over a river and times the descent. If the rock takes 2.09 seconds to hit the water, how high is the bridge? Okay, I actually did this. If you ever drive Highway 97 down through Central Oregon, let's see, it's actually the quickest way to get to Interstate 5 in California, although I wasn't going that far. But there's a place where Interstate or Highway 97 crosses something called the Crooked River Gorge, and there's actually a rest area there, and you can walk out on the bridge. But it looks like there's, it's a fairly narrow chasm, and the water is flowing down there in the bottom. And there's this bridge up there, and it's an old bridge. I don't know when it was made, but it's kind of a neat old thing. And you can stand up there on top and drop a rock from the bridge and have it drop into the water. I always check first to make sure nobody's fishing down there, because this is a popular fly fishing stream, but I didn't hit any fishermen as far as I know. So let's see how we can use one of our equations to figure this out. And the one I'm going to use is just the y equals y naught plus v naught y t minus 1/2 gt squared. Okay, now I'm going to let y equals 0 down here at the bottom. And so that'll be the final position of the rock. So this is going to equal 0. And I'll let y equal y naught up here from the height that I dropped the rock at. It says I drop the rock. Okay, when you drop something, its initial velocity is 0. So that thing is equal to 0. And what I get when it hits the bottom, I'll have 0 for the final height is going to equal y naught minus 1/2 gt squared. And I know g, t happens to be the 2.09 seconds. So if I solve this for y naught, I just get 1/2 gt squared is equal to y naught. Then I plug in the numbers. 1/2 times 9.81 meters per second squared times 2.09 seconds, which I square. Now, that initial height would then be, let's see, unit-wise, I'll have seconds squared when I square this second term, and those will divide with the second squared here, and I'll just end up with meters. And so we'll find out how high that bridge happened to be above the water. Wow, is it that high? No, that's not that high. Actually, 21.4 meters. And if I multiply that by 3.28 feet per meter, that's a conversion factor for converting units there, I would get about 70.3 feet. Now, I don't actually remember how long it took for the rock to fall, and I did not measure it with a stopwatch. I dropped the rock and went 1001, 1002, 1000, and it took closer to 3 seconds or something like that. So I just don't happen to remember what it was. I should do it with a stopwatch next time I'm down there, except I don't know, I probably won't. Actually, I don't usually stop at that rest area, so usually just go right by it because it's not far from either Redmond or Bend, and towns are usually nicer. So there's a sample free fall problem. Another one, actually, we're about out of time for today, but that's an introduction into free fall equations. They are in this little area of your formula sheet. And so these are with up being positive. Sometimes you can flip things, but I think when I solve problems, I'm usually going to let up, keep up as positive and just stay consistent that way. Because if we start changing directions, things can get a little bit confusing. Although if let's see, at times it's handier just to let down be positive. And then on this problem, if I wanted to let down be positive, I'd say, all right, down is positive. I'm going to let y equal 0 here, and this will be y final, and do something like that. You might experiment with that. They may do an example in the book like that, so you could check it out in there. But I'm going to mostly stick with up being positive. So Monday we'll do several free fall problems, and then starting Tuesday we're going to be dealing with projectile motion, which is where you launch a projectile at an angle and it'll have both x and y velocity, and we'll see how to solve that. So we'll go on from there. Okay. Does anyone have any questions?
I ask this like every day, but do you know when the sig fig quiz is going to be out?
Oh, I'm glad you reminded me. I'll put it up today, and I'll give
Oh,
you
yeah.
till next Friday for it. So, yeah, good. I'll do that right after class as soon as I start rendering my recording here. Yep, we can do that.
And there's a homework assignment out as well.
I will be putting, yeah, another sapling assignment up. I have to post that as well. So, yep. They're enough unrelated that it shouldn't be hard to do both of them at the same time, I think. Okay. Otherwise, have a good weekend, and I'll see you Monday.
Thank you.
Mm-hmm.